Alright, we have some practice problems from our exponential functions. Alexis deposits a $150,000 court settlement into an account that earns 4% interest compounded weekly. What will the account be worth in 10 years? So the first thing is to make sure you understand what formula we're using here. It says compounded weekly, so that's compounded periodically. So that's A of t equals p times 1 plus r over n raised to the n times t. So we need all those things. So p is the amount she starts with, which is $150,000. The 4% there is the interest rate, and we'll use that as r of 0.04. It says compounded weekly. How many weeks are in a year? 52. And t is 10 for 10 years. So we have everything we need. So a of 10. Let's clean that up a little bit. A of 10 will be equal to 150,000. There we go. Times 1 plus 0.04 divided by 52, and that'll be raised to 52 times 10. So we're going to put that in our calculator and get some type of dollar amount back. So follow along with me and let's see what we get. Looks like I'm getting $223,739.30 when I round that off. Alright, using the right formula is important, and making sure you can put it in the calculator and get what you want is important. Second one here. Barrett places $1,200 into a continuous interest account 4 years ago. The account is now worth $1,500. What is the interest rate? So a little bit different setup. So let's see here. We've got continuous interest problem, which is A of t equals p times e to the rt. So let's see here. We have an ending amount. So we have an ending amount of 1,500. We have a starting amount of 1,200. We have e, which is a constant. We don't have r, but we have the time, 4. So in this case, the p was 1,200, the a, the ending amount, was 1,500, and the t is 4. The thing that we don't have is the r. Okay, so let's kind of figure this out. 1,500 divided by 1,200 is 1.25, and that'll be equal to e to the 4r. So we can turn this into a natural log because we want to get this exponent out. So we'll say 4r equals the natural log of 1.25. And let's just go ahead and put that in the calculator. R will be natural log of 1.25 all over 4. So in the calculator, that gives me 0.0558 when I round it off, and if you like, you could say that as 5.58%. Okay, so we were given information and asked to find a piece of that formula, which is kind of the whole point of applications, to be able to rewrite and remanage the material. Okay, next problem, number 3. Jasmine starts a butterfly farm with a population of 100 butterflies. She knows the butterfly population grows at a rate of 6% per week. How many butterflies will she have after 10 weeks? So let's see here. This is a growth problem. So we can say A of t equals little a times b to the t. So let's see here. Little a is 100. That's our starting amount. And it says the B here, it grows at 6% per week. So that would be 100% of what she already has plus another 6%, or 1 plus 0.06. So our B will be 1.06. So, and it says we're looking for 10 weeks, so T will be 10. So we'll just plug all that in. A of 10 will equal 100 times 1.06 to the 10. So let's see how many butterflies she has at the end of 10 weeks. So it looks like 179 butterflies. Good stuff. All right. Number 4 down here. A Midwest county has a population of 245,000 in 2020. When it is discovered that the water supply is contaminated, residents start to leave the county at a rate of 7% per year. What is the estimated population in 2030 if this trend continues? Okay, so this is another growth decay. So let's see here. We have, my computer has frozen up for a second. It looks like we're back. So another growth decay problem. So let's see here. We'll have A of T equals little a times B to the T. So A would be the starting population of 245,000. B, it says they're leaving at 7%, so that's the 100% that's there minus 7%. If you like to change that to decimal, it'll be 0, when we subtract that, we'll have 93%, which we can change to a decimal and use 0.93. And it says, what will the population be in 2030? That is 10 years from now, so T will be 10 again. So A of 10 equals 245,000 times 0.93. Remember, if the population is going to decrease, we need a B, or an exponential rate, less than 1, and it'll be raised to the 10. So we're going to put that in the calculator. And let's see. Should be less than 245,000. It is. I get 118,000 and let's say 576 would be the population. So that's around half of what it was. A big change there in 10 years. All right, what's our next problem? The element math 19 has an exponential half-life of 13 years. How much of a 20 kilogram sample is left after 3 years? So again, with the growth decay formula, A of T equals A times B to the T. So let's see here. We have that the half-life is 13 years, but we don't have an actual rate here. So we need to find that rate. So I'm going to set it up, and I can use the 20 kilogram sample here if I want to, and say that I'm going to end with 10 kilograms if I start with 20 kilograms. So the big A would be 10, and the little a would be 20. I don't know the rate B, but I do know that this change happens in 13 years. So the formula I'm going to solve is 10 equals 20 times B to the 13. So I'll divide out the 20 and I'll have 1/2 equals B to the 13. And you may remember that we decided to raise both sides to the 13th root to get rid of that exponent. So B will be approximately, and let's use 4 decimal places, but 0.5, and we're going to take the 13th root of that. So 0.9481 is the B that I'm going to use. So let's come over here. We're going to say that after 3 years, we started with 20 kilograms. Our rate was 0.9481. That's a rate less than 1 because it's decreasing. And the time that we're putting in here is 3. So 20 times 0.9481 raised to the 3. Okay. So I'm going to retype that in my calculator to make it look more like what's on here. And once again, if you don't get what I get, then we need to talk about it and how you put it in the calculator. But I get 17.04 kilograms, I guess, is a good enough estimate. Okay. Okay, so let's see here. I think this is our last problem, maybe. Number 6. A radioactive element decays at a rate of 21% per year. What is the half-life of the element? Okay, so let's see here. Let's try and set something up here. The formula we're using is A of t equals A times B raised to the t. Something we don't have here is the little a, the starting amount. So it's not mentioned any amount in the problem, so let's just start with a unit of 1. Okay, and it says here that the rate, B, says it decays at a rate of 21%. So we can say that as 1 minus 0.21. So I guess my B will be 0.79. And what I'm trying to find here is a T. So if I look at the formula here, A equals A times B to the T, I need everything except for that T, that time, because that's what I'm going to try and solve for. Well, the only thing they gave me was a rate, and but I'm talking about a half-life, so I can pick any starting amount I want. So I start with 1 for little a. If that's the case, I can end with 1/2 for big A. Now I could have started with 2 and ended with 1. I could have started with 50 and ended with 25, as long as I set it up as a ratio of half that original amount. I usually start with 1 and end with 1/2 because whatever I put in for the little a, I'll have to divide by it. So it just saves an extra step. So the problem looks like that I'm going to set up 1/2 equals 1 times 0.79 to the t. So I've just got to figure out a way to get t by itself. And that's where my logarithms come into play. T equals the log of base 0.79 of 0.5. So I need a change of base formula. So log of 0.5 over log of 0.79. That's an exact answer from what we've got. We have no idea if that's a big number or not. Probably not a big number. But let's see here. It comes out to be 2.94, and that would be years, which makes nice sense because we said that it was decaying at 21% per year. So if you did that about 3 times, you should theoretically be less than half. Remember, it's not compound, 21 plus 21 plus 21, so 3 years doesn't mean 63% because the new amount is different than the year before. But in this case, the half-life would be almost 3 years, 2.94. Okay. All right, some good examples.